I'm Anil Kumar, and in this video we are going to discuss most of the things which you need to know about curve sketching. So we have a function y equals to x over x squared plus 9. Let us try to find all significant characteristics of this function so that it can be sketched properly. So what are those characteristics which you should be looking for? Let us try to list them and then we'll find them one by one. So first we should actually find the intercepts. So we can find y-intercept for the given function. We can also find x-intercept. Now my recommendation is that x-intercept is not a must. Sometimes it could take a lot of time, so that is not critical. Y-intercept is kind of simpler, where you have to just substitute x equals to 0, right? So if I substitute x equals to 0, then I get y-intercept. So for me, y-intercept in this equation, x over x squared plus 1 will be equal to 0 over 0 plus 9, which is indeed 0. Now since y-intercept is 0, we know x-intercept is also 0. So the point origin 0, 0 is on the curve, correct? So we get two critical points which happen to be the origin itself. Now the other things which we need to find is the local extreme values. So local maxima or minimum, that we can find by finding the derivative of the function. So what we can do is, let's write the function as f of x, right? So in that case, derivative of the function, when you equate it to 0, we get critical points, right? So we get critical points. And these critical points help us to find local maximum or minimum values, right? So let us find its derivative and then we'll see what local maximum minimum could be for the given function, right? So in this case, we have f of x equals to x over x squared plus 9. So the derivative will be equal to, let's write down the derivative here, f prime x will be equals to square of the denominator, which is x squared plus 9 whole square, derivative of numerator, which is 1 times x squared plus 9 minus x times derivative of denominator, which is 2x. So that is what you get. So this is minus 2x squared. You can kind of simplify it. Minus 2x squared means you get 9 minus x squared over x squared plus 9 whole square, right? So in this function you can notice that the denominator is never 0. Now so that means there are no vertical asymptotes. So this is a rational function. Even then we do not have any vertical asymptotes, since the function denominator is always non-zero, right? Now this function critical points for this function are plus minus 3, right? So these are the critical points. So the critical number which we get from here is plus minus 3, right? Which we get by equating the derivative to 0. So we have two critical numbers which are, so f prime x is 0 at two values. One value is plus 3, the other one is minus 3, right? So these are the two critical numbers for us. Let us analyze these two critical numbers and we can find whether we have local maximum or local minimum at these points or not, right? So the two critical numbers for us are at minus 3 and plus 3. You could actually do increasing and decreasing interval and find whether we have the derivative as positive or negative in the interval in between these two critical numbers. You could also test for maximum minimum, local maximum minimum using second derivative, right? So we'll do second derivative also and find point of inflection. Also we can figure out whether it is local maximum minimum or not. Well, in case we have we use the increasing decreasing interval, let me take some test points here to help us out figure whether we have local maximum or not. So let the test points be -4, 0 and 4, right? So if it is -4, square will be 16, and so this will be negative quantity. So we are expecting negative here. If it is 0, we have positive. If it is 4, it is negative, right? So that really means that the function f of x will be negative, means decreasing in this interval, increasing, and then decreasing, right? So that clearly shows that we have local minimum at -3 and local maximum at +3, correct? So we can always find the value of function at plus and -3 to get the value for local minimum and maximum. So let us find those values. So what we have here is f of +3 is equal to 3 over 3 square plus 9, which is 3 square is also 9. 9 plus 9 is 18. So it is 3 over 18, which simplifies to 1 over 6, right? F of -3 will be equals to -3 over -3 square plus 9, which will also reduce to 1 over 6, but with negative signs. This is negative, so negative 1 over 6, right? So these are the two values which you will get for local maximum and minimum, right? Now let us analyze the second derivative. So with the first derivative, you get critical points and relative maximum minimum values. Now we'll find the second derivative of the function equated to 0, and we are trying to find point of inflection, correct? So let's find the second derivative. Second derivative for the function, we could use this first derivative here, right, is equal to square of the denominator, right? So square of the denominator will be x square plus 9 to the power of 4 times derivative of the numerator, which is minus 2x times x square plus 9 whole square minus the numerator, which is 9 minus x square, times derivative of the denominator, right? Denominator will be 2 times all this. So let me write the numbers later. 2 times, we'll write 2 here, okay? 2 times x square plus 9 times derivative of x square, which is 2x. So that becomes the derivative for the given function, right? So from here we can actually simplify it a bit. So we get minus 2x is common, so we'll write minus 2x as common. Also x square plus 9 is common. X square plus 9 is common. So we are left with x square plus 9 from the first term, and from the second term we are left with 2 times 9 minus x square. We have already taken the negative sign outside as common, right? So we'll make it positive, right? Okay, so we have positive, since minus 2x has been taken outside, 2 times 9 minus x square, correct? Everything divided by x square plus 9 to the power of 4, right? So that becomes the second derivative, which we can further simplify. So we have minus 2x, x square plus 9, and in the bracket we have x square minus 2x square is minus x square, so we have minus x square, and 9 plus 2 times 9, 18, which is 27, so we get plus 27 here, right? So that is what we get as the part of the factor, x square plus 9 to the power of 4. Now the critical points here are, this part is 0 for x equals to 0, right? Or here we have 2 zeros, right? So which are at square root of 27, right? So we have the point of, so f second derivative, f double prime x is 0 for x equals to, let me use a different ink here, 0 when this factor is 0. This is never 0. Or when minus x square plus 27 is 0, right? That means it is square root of plus minus square root of 27. Is that okay? Of course, square root of 27 can be written as 3 square root 3, right? So we can write 3 square root 3. So this is could be simplified as, or let me say at 0 and plus minus 3 square root 3, right? So that is square root 27. So these are the 2 points where we could have, rather 3 points, where we could have point of inflection, right? So let us test them out. To test point of inflection, what we do is we check whether the derivative is positive or negative on either side of these points, right? So let me push this paper a bit. Okay, so we have 2 points here, which are, rather 3 points. So let me put 0 in the center, right? And then we have 3 square root 3, and we have minus 3 square root 3. Perfect. Now the test points could be selected as, you can say, minus 1, plus 1. And we could have, let us say, a big value, let's say 10, right? So 10 and minus 10, correct. Now if I substitute these values in the function itself, if I write, let us say 1, now in that case what you notice is that for a positive value of 1, this is negative. Now for a positive value of 1, this is positive. So you get a negative value, right? So in this part you get a negative value. Since it is negative, it is going to be concave down, right? So if I substitute minus 1 here, right? So if I substitute minus 1 here, in that case, what happens? In that case, what we get here is this becomes positive, right? So minus 1 times this remains at positive, so it is positive, right? So it is kind of like this, correct? So it is at 0. What we see at minus 1, that the concavity changes. So we do have a point of inflection at this point. Now let us test the values minus 10 and plus 10. So if you write plus 10 here, then this value is negative. 10 squared is 100, which is negative. Negative and negative gives you positive, so we get concave up, right? So what we're trying to find is the second derivative, right? So it is positive here, right? So it's positive, negative, positive. If you substitute minus 10 in that case, minus 10 will make this negative, minus 10 will make this positive, right? So minus minus, and therefore it will be negative. So it will be this, kind of like this. I would like you to substitute these values and check with calculator, correct? But here we get 3 points of inflections, right? So we can write down that the point of inflections for us are at x equals to all the 3 points, which are minus 3 square root 3, 0, and plus 3 square root 3. So we get point of inflections, right? And that is from the second derivative. Now I'll also like to tell you that you could have found local maximum minimum using the second derivative. If you are on the left side of minus 3, then you see that the second derivative is, if you're close to minus 3, then the second derivative is positive, right? So that means you have a local minimum. But if you are on the right side of minus 3, that means around 0, then in that case, second derivative for you is also 0, right? So you do not have any point of maximum minimum at 0. However, if you test the value at 4, which is on the right side of 3, then at 4, if I substitute 4 here, then what I get here is negative value, and therefore this is going to be a positive, right? So we could actually write decimal value of 3 square root 3. That will help you to understand better. 3 square root 3 is basically equals to 5.19, right? So this is kind of 5.19, right? So you could say minus 5.19. So when I say close to minus 3, then I'm here. Do you understand? So that is negative. Close to plus 3 is on this side, so positive. And that positive gives you local maximum, negative gives you local minimum. I hope that is absolutely clear. In any way, what we found here is a couple of these things which are local maximum minimums. And one more important thing to find is the asymptotes, right? So asymptotes, let me write down here. Now the order could be different. At times, normally, we prefer to find asymptotes before getting in for the derivatives, right? Since it is a rational function, we do expect asymptotes. So what we get here is that as x approaches positive infinity, right, then y approaches, since the denominator is 0, is approaching 0, right? It is important to check that if it is positive, then it approaches from the positive side. However, when x approaches negative infinity, then y does approach 0 itself. But if it is a negative high value, it is negative. So it approaches from the negative side. Now that is very critical to understand. So you could sometimes say that gives you behavior. Let me write here, behavior near asymptote, right? So let me squeeze all these things because I have just that limited space, and I prefer to just give you solutions and thinking in that limited space. Okay, so now from all this we can kind of sketch the function, right? Now here is the function. So what we found basically is that it is approaching that is the horizontal asymptote, y equals to 0, right? So let me write here horizontal asymptote, right? Which is indeed y equals to 0. However, it is approaching from the positive side when you approach positive infinity, and from the negative side when you approach from the negative infinity, right? So that is important. Second, what we found is that local minimum is at minus 3, maximum is at plus 3. So let us say this is 3 for us, right? So this is 3 for us, okay? These dotted lines are not the asymptotes, okay? These are my guidelines. And the point of inflection is at 0, which is here, and it is minus 5.9. Let us say minus 6 twice away, kind of like this, right? So that is your point of inflection. And since I've squeezed in, my graph may not look as good, right? But I hope with that graph you will kind of get an idea that how it should be, right? So it is like this. So it is concave down from here, and it is concave up from here. Do you see that? Concave up from here, and all throughout, as we are saying, up to 0, it is concave up, right? So do you see that part, right? And then it is concave down till the next point of inflection, going to a maximum value here, right? So it is kind of concave down to the point of inflection, and here it is concave up. Concave up. Do you see that? So that makes a neat graph for the particular function, and that is how it should be drawn. So I hope these steps are absolutely clear. That is x and this is f of x. So I hope this limited space approach has just helped me to fit in everything perfectly. Thank you, and you can subscribe to my videos and learn a lot. Let me summarize the steps to sketch a function in general using calculus. So what you should do is, first step is understand the function. So we say it is a rational function, right? So when it is a rational function, important thing here also becomes is asymptotes, right? So I forgot about asymptotes initially. Let me begin with that. When we review, rational functions could give you asymptotes, right? It could be vertical asymptote, oblique asymptote, or horizontal asymptote. Is it okay? check for these asymptotes. In our case, we had the horizontal asymptote. Then find x and y intercepts. Y-intercept is a must, that is, you may leave it, right? So you may not find x-intercept for most of the graphs, right? That is not important, but if you can, as it was easy, we did. Then you find local maximum and minimum, right? So sometimes we say relative, sometimes we say local maximum minimum values. Then you find point of inflection. That is to say, analyze the first derivative, find the critical points, analyze the second derivative, check the critical points for local maximum minimum and also for point of inflection. And then you have some important points to sketch the graph. Behavior near the asymptotes actually helps you to identify or make sure that you are on the right path, right? Calculating values is important for the accuracy of the graph. With this, I think if you follow these steps, you should do perfectly well in sketching any function using calculus. Thank you and all the best.